Alrighty, howdy folks. So the next thing to do is chapter 12, section 3, the dot product. I'm sure you have used dot product of vectors before, right? But yeah, let's see a few more things here perhaps. Okay, doke. The definition. Ooh, it's a big one. If A is given by the components A1, A2, A3, so obviously this is a three-dimensional vector. And similarly, B is B1, B2, B3, then the dot product of A and B is a scalar quantity. So I think that's an important thing to recognize. When you take the dot product of two vectors, what you get is a scalar, some kind of a number. Even though vectors themselves are, magnitude and direction, when the moment you take a dot product, what you get is just the number, scalar. Cool? Okay. And how do you figure that out? A dot B is simply A1 B1 plus A2 B2 plus A3 B3. Basically, what's that? We are taking the first component of A and multiplying that by the first component of B, giving you A1 B1 plus, and you are adding to it the product of the second component of the first vector with the second component of the second vector, and so on. That's the idea. Cool? As simple as that. What else? Properties of this dot product. If A, B, and C are vectors in V3, that means a vector space, three-dimensional vector space. I think we could have called it R3, meaning at least in this course, we are dealing with only real vectors, right? So R3. And C is a scalar. Then these are the things that are going to happen. A dot A is simply magnitude of A square. What? A dot A is magnitude of A. Maybe I should have put a vector there. Square. Is that obvious? Yeah, because check this out. If instead of B we were to have A dot A is what we would have, right? Then this would be A1 times A1, and this would be A2 times A2 and A3 times A3. That is A1 square plus A2 square plus A3 square. Well, isn't that the square of the magnitude of the vector A? Yep. So that's something to keep in mind. Another one. Vector A dot B is equal to vector B dot A. So that means the dot product is commutative. And distributive property also applies. A dot B plus C is A dot B plus A dot C. And CA dot B, where C is the scalar, you can just yank that C out and take the dot product of A and B and later multiply by C. Okay, and so you can do that, or A dot CB. Some of these are kind of intuitively obvious, but it's not a bad idea to go over them. And A dot 0, anytime you take a dot product with the 0 vector, you get 0. Isn't that obvious? Let's see. Let's go back to this A dot B thing, and instead of B, let's say we were to have had 0 vector, then A1 times this component B1 would have been 0. B2 would have been 0 and B3 would have been zeros, right? That's what a 0 vector would be. Its components are all 0. So A1 times 0 plus A2 times 0 plus A3 times 0. Obviously, that's a 0 plus 0 plus 0, which is 0. So this property is obvious. Okay, cool. With that, let's go to a theorem. If theta is the angle between the vectors A and B, then A dot B is magnitude of A times magnitude of B cosine theta. Okay, that's another important one. So A dot B, there's another way of finding out this dot product, which is multiply the magnitudes of both the vectors, and also multiply them by cosine of the angle between them. Now, there's something that I need to warn you. Typically in 2 dimensions, when we have two-dimensional vectors, measuring the angle between them is a piece of cake, right? It's clear, you can clearly see it. But then for three-dimensional vectors, two of them, what exactly is this angle between the two vectors? Are you looking from the front or from the side or from the top? Which way? So that's not so clear. So I will, at a later time, I will explain to you what I'm, how to take care of that. But right now, just at least be mindful of the fact that the angle between two vectors is not so straightforward when you're talking about two vectors that are in three dimensions. Okay. All right. Next, corollary of this theorem is, if theta is the angle between non-zero vectors A and B, then cosine theta is simply A dot B over magnitude of A times magnitude of B. That should be obvious, right? We are just simply taking this equation and dividing both sides by magnitude of A and times magnitude of B. And that's how we get this cosine theta. But that's a very useful one. This formula of cosine theta is the dot product divided by the products of the magnitudes. That's a useful one because oftentimes we would be required to find the angle between two vectors, and then we will employ this formula. Cool. All right, another theorem. Two vectors A and B are orthogonal if and only if the dot product is equal to 0. Does that make sense? Two, by the way, if and only if. What in the world is if and only if? I think I have mentioned, if you have had a class from me before, you probably know this, but let me repeat this. If and only if is in mathematics doesn't have the same usage as if and only if in regular day-to-day language. For instance, mom would wag her finger and say, "Hey, Tommy, you will get to play with your Nintendo if and only if you clean up your room." That means, like, that's a finger wagging thing. You better do this, otherwise you won't. But in math, if and only if has a completely different meaning. And what is that? This should be interpreted as, if two vectors A and B are orthogonal, then A dot B is equal to 0. Cool. And it is also true that if A dot B is equal to 0, then the two vectors A and B are orthogonal. So that means both the conditional going from left to right and going from right to left, what is called the converse, they are both true. In that case, where both the conditional and the converse are true, we use this if and only if. P implies Q and Q implies P can be replaced by P if and only if Q. Okay? All right. So, like I said, two vectors A and B are orthogonal if and only if A dot B equals 0, means if A and B are orthogonal, then their dot product is 0. If A dot B is 0, then the vectors are orthogonal. As simple as that. Cool. Next, also, A dot A, according to this, we already saw that property, that A dot A is equal to magnitude of A, the quantity square, right? Can we get to that using this formula for dot product? Yep, we can. A dot A is equal to magnitude of A times magnitude of A times cosine of 0. What? What do I mean by cosine of 0? Where does the 0 come from? Well, cosine of what? Cosine of the angle between the two vectors, right? But here, the two vectors are the same vector, A and A. What's the angle between vector A and vector A? 0, because one vector falls right on top of the other, or in other words, one vector is parallel to the other vector. A and A are parallel to each other, and so their angle, the angle between them, must be 0. So we have A dot A is nothing but a magnitude of A times magnitude of A times cosine of 0. Cosine of 0 is 1. Therefore, this is equal to magnitude of A, the quantity square. Cool? All right. Now, the implication of this is if we were to go to those standard basis vectors, I, J, K, what's up with them? Well, I dot I must be equal to 1. I must be equal to 1? Well, does this look like A dot A? Yeah. And so that must be the magnitude of I times magnitude of I. What's the magnitude of I? I is a unit vector. So its magnitude must be 1. Oh, okay. So 1 times 1 times cosine of the angle between them. Well, the cosine of angle between the same vectors is 0. So this is just 1. Right? 1 times cosine 0 or 1. Similarly, j times j dot j is equal to 1, k dot k is equal to 1. And further, and not only that, I dot j is equal to j dot I. Dot product is commutative, and that is equal to 0. Explain to me why this is. Well, we already learned about that theorem that says two vectors A and B are orthogonal if and only if A dot B is equal to 0. Well, we could apply that. Or could you talk about it using this concept of cosine theta? I dot j, what is the angle between I and j? 90 degrees or pi half radian. So what happens? Well, in that case, we have 1 times 1, magnitude of I times magnitude of j, 1 times 1 times cosine of 90 degrees. Cosine 90 degrees or cosine of pi half radian is 0. So therefore, that's going to be 0. Similarly, j dot k equals k dot j, which is 0, and I dot k and k dot I, they are also 0. Cool? That's the thing. And now some simple silly problems. I'm sure this is all piece of cake to you. Find A dot B. Duh. You take the first component, multiply by the second component, plus second component times second component here, and like that. And just is arithmetic. Turns out to be -1. Next, it's a sort of a similar problem, but instead of giving it in that uh, angle bracket notation, we got a slightly different notation. And so we got 3i plus 2j minus k. Well, who's stopping us from writing this as 3 comma 2 comma -1? Could we write this in the angle bracket notation? Um, huh, I didn't do that, eh? What's with this looking? And I go from one computer to the other, things look different. Got it. Oops. I gotta screw that guy. I gotta screw this guy. Okay. Oh, brother. Implication of that is that. Sorry about that, guys. Okay. So here, what we can do is we can reinterpret this as angle brackets and work with it, where we say this is 3 comma 2 comma -1. And how do we write this guy? Are you with me? When the vector was 3i plus 2j minus k, I said we can write that as 3 comma 2 comma -1 in angle brackets like that. How are we going to write this? Be a bit careful though. for I, okay, that's 4, comma, there is no j component. That means the jth component must be 0, right? That's, as long as you do that, you are okay. And the next thing is, I didn't do that, it looks like. That's okay. So we'll take the I versus times I, 3 times 4, plus 2 times 0 for the jth component, and -1 times 5, right? That turns out to be 7. Or we can do a longer solution. I just want to do this to show you. This might come in handy maybe at a later time. Okay. Crud. This has done that too. Okay. Okay. When I created this on my desktop, everything was fine. But when I transferred it onto the laptop to do this recording, that's when the alignment got messed up. Okie dokie. Um, so we have A dot B, is that right? So check this out. Can we apply the distributive property? That means, can I first take this vector 3i and take a dot product with 4i plus 5k plus the 2j dotted with this one and distribute like that? It's almost like this, what's the multiplying method that we use, the distributive property for regular kind of a plus b plus c times some p plus q. You can do that. It works more or less the same way. So the first would be 3i dotted with 4i. So that means 3 times 4 times I dot I. 3 times 4 times I dot I. Then 3 times 5 I dot k plus 2 times j 2 times 4 times j dot I, and so on. Okay, so we can distribute out like that. And at this stage, we will recognize that I dot I must be just 1. Notice that's only true because I and I are not only the same vector with a 0 angle between them, but because they are unit vectors. Okay, I dot I is 1. However, I dot k is 0. J dot I is 0. J dot k is 0, because these vectors are all mutually perpendicular, and so their dot product would be 0. So we would be left with only k dot k and this I dot I component. So that's just 12 minus 5 is 7. This is of course a longer way of working this out. This is not something that I'm recommending that you do to solve a problem like this. But when it comes to doing calculus with vectors at a later stage, stuff like this you will need. Okay, all right. Problem, find A dot B given magnitude of A is 80, magnitude of B is 50, and angle between the vectors is 3 pi over 4. If you need to, please pause and see if you can solve this problem. What are you asked to find? A dot B. What are you given? Magnitude of A, magnitude of B, and angle between them. Duh, isn't that simple? A dot B is equal to magnitude of A times magnitude of B times cosine of the angle between them. And if we apply that, ta-da, we get this. As simple as that. Okay. Next. Find the angle between the vectors A and B. Here we are going to find the angle between two three-dimensional vectors. And of course, there's a simple formula like cosine theta is A dot B, and if we apply that, we get the answer. That means theta must be 79.26. But should I talk about this now? Yeah, maybe. Okay, pretty soon I think I'll cover it. So as a problem, this is fairly straightforward, procedural, right? Find A dot B and find a magnitude of A by using that A1 square plus A2 square plus A3 square, the square root of that, and so on. That's a straightforward one. Okay. The next kind of problem is determine whether the vectors are orthogonal, parallel, or neither, given these two vectors. How do we do that? Apparently, we need to find, we're given two vectors and we're asked, hey, are they orthogonal to each other? Are they parallel to each other or neither? Any thoughts about that? And why is that problem showing up here in the dot product section? Well, here is the idea. A strategy is to find the dot product of the two vectors. And if the dot product is equal to 0, then the vectors are orthogonal. Would you agree? Two orthogonal vectors have a dot product of 0. Yep, that's what would happen. If the dot product is 1 or negative 1, then the vectors are parallel. Now that's what? Equal to 1 or negative 1. What's with the negative 1? Oh no, I think I may be wrong here. I should not say equal to 1 or negative 1. Okay. Why? Neither otherwise. So in this case, this turns out to be negative 1, but if I think I should be careful. If the dot product is simply equal to the magnitude of the dot product is equal to the product of the magnitudes of the vectors. The vectors are parallel. Yikes. Sorry, folks. Is equal to the product, the magnitudes of the vectors, then they are parallel. In fact, we can say the absolute value of the dot product. The absolute value of the dot product is equal to the product of the magnitude of the vectors, then they're parallel. Would you agree with that? Let's see. See, the thing is, let's say two vectors, 2i and 3j. You and I know that they are clearly orthogonal to each other, right? So 2i and 3j, so 2 times 3 is 6, I dot j, so that would be cosine of, no, what? Okay, 2i and 3i, are they parallel? That's what I think I meant to say. 2i and 3i, are they parallel to each other? Yeah. Then what's the dot product of 2i and 3i? Would be 6, right? But what's the length of 2i? Magnitude of 2i? 2. And magnitude of 3i is also 3. See, in that case, the dot product magnitude is the same as the product of the magnitudes. So that's when they are parallel. Or if you take 2i and negative 3i, then their dot product is negative 6. Uh, and you take the absolute value of the dot product, you get a 6. And that's the same as the product of the magnitudes. Magnitude of 2i is 2, magnitude of negative 3i is 3. And so 2 times 3 is 6. Absolute value of 2i times negative 3i is also 6. That's the thing. I should have been careful. Sorry about that. Neither otherwise. So it turns out this is mm, mm. So the conclusion is, dang man. So we cannot say that, right? So this is neither. Clearly the magnitude of 5, 4 and 2, that's pretty, 25 plus 16 plus 4, that's something. So definitely that's not going to be, nope, 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 nope. So neither is the answer. Boy, did I goof big time. I hate that. Sorry, guys. Let's move on to the next one then. Yeah. Direction angles and direction cosines. This is an important concept. Maybe now I can talk about what I've been alluding to. Be careful about what the angle between two three-dimensional vectors is. Okay. The angle between these two three-dimensional vectors, you need to be careful, meaning, let's try to understand that. If you notice this alpha is the angle between the x-axis, that is the I vector, and this vector itself, the A vector. But then how do you measure it along in which direction? Are you looking at this from the front, or from the top, or from the side? And here is the idea. Please pause this video if you need to. Grab two pencils. Okay, grab two pencils and come back and hold those two pencils now in such a way that the bottoms of the pencils, the eraser side, okay, they are both touching. The two bottoms are touching. Okay, and the pencils themselves are making a certain angle. Cool. Now notice, together you can rotate that in both of them in any direction you want. So if we are trying to say the angle between these two pencils, which represent two three-dimensional vectors, is, then we have to talk about a plane that contains both those pencils. Let me repeat that. This concept is absolutely crucial, so I'm taking time to go through this. Okay. there is a plane that contains both the pencils. If you don't believe me, take a cardboard and rest it on and make sure that the cardboard touches, a flat cardboard touches both the pencils. Well, isn't that the plane that contains both the pencils and both the vectors, that is? Are you with me? If you take a cardboard, you can get that cardboard to sort of touch both the pencils, right? And so that means that cardboard represents the plane containing both the vectors. Now, the moment you talk about a plane, you can look at that plane from a perpendicular direction. You can look parallel to the plane or look perpendicular to the plane. Now look at the angle in perpendicular to the plane. Whatever that angle is, that is the true angle between the two vectors. It is not the front view or the top view or the side view. It is the view that is perpendicular to the plane containing both the vectors. Man, that's a mouthful. Let me repeat that. The angle should be measured from a view that is perpendicular to the plane containing both the vectors. Perpendicular to the plane containing both the vectors. That's the idea. Okay. So alpha is the true angle between the x-axis and the vector. Beta is the true angle between the y-axis and the vector, and similarly gamma between z and the vector. Now, while that is one thing, there's one more aspect that we need to cover. Would you agree that alpha, even if you look at say alpha, we can measure an angle that may be between 0 and 180, or if we go in the opposite direction, uh, we could get something between 180 and 360. What do I mean by that? Okay, let me put it in a slightly different way. Can I say the angle between two lines is 30 degrees? Well, if you measure it in a certain direction, yes, that is 30 degrees. But the same angle, if you were to go the other way, isn't that 330 degrees? So the question is the angle 30 degrees or 330 degrees? Or is the angle 150 degrees or 210 degrees? Right? We always get this question. Is it 179 degrees or 181 degrees? And here the concept is clear. You always take the angle between 0 and pi. That means 0 and 180. Okay. So the direction angles of a non-zero vector A are the angles alpha, beta, and gamma in the interval 0 to pi that A makes with the positive x-axis, positive y-axis, and positive z-axis, respectively. Cool? This direction cosines are pretty important. Now, how do we find these direction cosines? Simple. If our vector is a1, a2, a3, its x component is a1. Would you agree? Its x component is a1. So that means if we were to that a1 component along the x is something that can be written as a vector. Let me repeat that. Oh, I drew this one, right? By the way, would you agree the distance from the origin to this point, that is a1? Now, can I write that as a vector? If I were to start here, my tail of the vector is here and the head of the vector is here. Isn't that a1I? Right? So if we do A1 over the magnitude of A, then that would be cosine alpha. I'll show you exactly how we can get that. And cosine beta is A2 over A, magnitude of A. Cosine gamma is that. And, whoa, what happened? I thought I showed that, man. Ah, um, let's see. Okay. Yeah, cosine square alpha plus cosine square beta. I'll show that here. Thought I had something else that I appended to this. A1 over magnitude of A. Ah, got it. Let's cosine alpha. I have a pen I can write with. Okay, A dot B is equal to magnitude of A times magnitude of B times cosine of the angle between them, right? Okay, now what if I were to do A dotted with I? That means the unit vector I. Then we would have magnitude of A times cosine theta. Because magnitude of B is just 1, magnitude of I is just 1, we will get this, right? So cosine theta is going to be A vector A dotted with I divided by the magnitude of A. Okay, so what we are trying, and that is exactly what we are doing here. When I say theta, the theta is nothing but the direction angle alpha, direction cosine angle alpha here. And so if we take the dot product of A, the vector, with I, we get alpha, cosine alpha. So that's what this is doing. This is A dot I, but A dot I is just going to be A1 over the magnitude of A. Are you do you agree with me that A dot I would actually be equal to A1? Yeah, because A is A1, A2, A3. If we take the dot product with I, which is 1, 0, 0, A1 times 1 plus A2 times 0 plus A3 times 0, which is A1. See, that's how we get this one. I wish I had written this down nicely. Okay, but that's the idea. Cool. All right. Find the direction cosines. Some silly problem. Simply A1 is the x component is 6, divide by the magnitude of that, and you get 6 over 7. And if cosine alpha is 6 over 7, alpha must be 31. I used a calculator to figure that out. Similarly, cosine beta and beta gamma, you can figure that out. Okay. Uh, okay. Ooh, negative 2/7. Yeah, that you need to be careful. We get 106.602. Don't use the 360 minus this value, which is some, oh boy, 253.4 or something like that. Yeah, you need to use the value between 0 and 180. 0 and pi. Okay. Okay. Probably one other very important concept here. Maybe here is where I explain that. All right. The scalar projection and vector projection of B onto A, we need to figure that out. And that, look at this figure. What is that? What is the scalar projection of B onto A? Projection. To me, projection is kind of like a shadow. A good example of a projection is, you guys shoot pool. Have you ever been to a pool hall and played pool? Now, imagine you have a pool table, and typically, right on top of the pool table, there would be lights, right? Projecting with the light focusing on the pool table itself so that it's all bright. Now, if you were to take the pool cue and keep it sort of horizontal, then the lights from the top will cast a shadow on the pool table, right? Will cast a shadow of the pool cue onto the table. That's the projection of the cue onto the table, that shadow. Now, if you were to tilt the cue at an angle, then the light would be projecting and onto the light would be casting a shadow of the cue onto the table, and that shadow is going to be slightly smaller in size than the cue itself, the length of the cue. When the cue was horizontal, the length of the shadow and the length of the cue would be the same, but at an angle, the length of the shadow would be less than the length of the actual length of the cue, right? So basically, when we are talking about B, think of B as being a cue, and its shadow is being projected onto vector A. That vector A is nothing but the pool table. Okay, so if the angle between the Q and the pool table, vectors B and vector A, is theta, then the length of that shadow, that is the scalar projection of vector B onto vector A. And what is that? That's just nothing but magnitude of B times cosine of that angle, cosine theta. And that is represented as component of B onto A, component of vector B onto vector A. Cool, that's a scalar projection. Now, what in the world is the vector projection? It's the same as that one, but written as a vector. So there's a small difference. The projection of vector B onto vector A and component of vector B onto vector A will have the same magnitude, but the projection happens to be a vector quantity. That's the whole idea. Okay, and here unit vector of A is E sub A, let us say, and that's nothing but the magnitude of the vector itself divided by the magnitude. The point I'm trying to make here is this, folks. Sorry, please pay attention. In order to find this scalar projection of vector B, guess what you need to do? You need to take the dot product of B onto the unit vector of A. That's why I'm going through with all of this. Let me repeat that. To find the scalar projection of vector B onto vector A, you need to take the dot product of vector B onto the unit vector along A. Right? A itself may not have a magnitude of 1, but if we divide the vector A by its magnitude, we get a vector which is in the same direction as A, but with a magnitude of 1, which is what I'm calling as the unit vector along A and representing it as E sub A. So the B dotted with E sub A is B, magnitude of B, times 1 times cosine of the angle between them, and that's exactly what the scalar projection is. I have a B dot A over this, but I can write this as B dot A over the magnitude. B dot A is equal to A dot B. So basically we are saying that the scalar projection is nothing but A dot B over A, or the dot product of B onto the dot product of B with, rather, the dot product of B with the unit vector along A is the idea. Cool. Uh, and how do we get that same thing represented as a vector? Well, if we know this magnitude, all we need to do is multiply by the unit vector. Let me repeat that. This projection vector, that the vector projection, because it is a vector whose magnitude we know from this component of B with respect to A, what we now need to do is take that magnitude and multiply by the unit vector along that direction. But do we know the unit vector along A? Yeah, that's the one that we just calculated as E sub A. So if we multiply this scalar component by the unit vector E sub A, we are done. We got the vector projection, and that's what we are doing here. But E sub A is nothing but magnitude A, vector A over magnitude of A, and so in the denominator we have a magnitude A square and A dot B A. So try to go over all of this and try to make sense of all of this. This is an important concept. I think I was a bit verbose on that one. I could have been more succinct, but I got a little too excited. Okay, anything else? Okay, simple problems. Scalar projection, apply that formula, A dot B over magnitude of A dot 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 8 nines. Then vector projection, just multiply by the unit vector, or in this case, we use this one. That's it, folks. All right. Thank you.